Hello there, students who happen to be 8th graders. We are in section 2.4, Biconditional Statements and Definitions. This part right here you do not need to write down. This is going to lead into what we're going to talk about today. Now, I'm not sure if any of you have fish tanks or if any of you deal with plants a lot, but the pH balance of different things. For example, if you have a fish tank, the pH balance in your water has to be a certain amount. Otherwise, if it's too acidic or too basic, your fish are going to die. The same thing is true with plants. Plants actually use pH to determine whether or not the soil is going to be too acidic or too basic. So, here's your chart on 0 to 14, acidic to basic. Now, we're going to just read these sentences here. The pH of a solution is a measure of the concentration of hydronium ions in the solution. So here's our first part. If a solution has a pH less than 7, it is acidic. So now I'm going to reverse it. If the solution is acidic, it has a pH less than 7. Notice that either way you write it, it's still true. So if I take the hypothesis here, if a solution has a pH less than 7, it is an acid. And then do the reverse of that, which is called your converse. If a solution is an acid, then it has a pH less than 7. This is called a biconditional statement. So here is your first vocab word. When you combine a conditional statement and its converse, you create a biconditional statement. A bi, which means two, a biconditional statement is a statement that can be written in this form. P, if and only if Q. So, if you have something that says P, if and only if Q, we write it with an arrow going both ways. What that means is that if you take if P then Q, and if Q then P, if both of these are true, which would be your conditional statement and your converse. If they're both true, we can write it like a biconditional statement. So let's take our original acidic and alkaline problem. If you can define an acid with the following biconditional statement, a solution is an acid if and only if it has a pH less than 7. So rather than saying the conditional statement and its converse, we can write it as one statement, which is called the biconditional statement. A solution is an acid if and only if it has a pH less than 7. So let's look at our first example. I want you to write the conditional statement and its converse within each biconditional. So in A, we have the biconditional statement, two angles are congruent if and only if their measures are equal. So let's write our two statements. Let's start with a conditional statement. So our conditional would say this. Two angles are congruent if and only if their measures are equal. We could say if two angles are congruent, then their measures are equal. So that's the conditional. What would the converse be? The converse would say if two angle measures are equal, then the angles are congruent. So why don't you try B yourself and see if you can figure out what the conditional and the converse are. So part B says, a solution is a base if and only if it has a pH greater than 7. Identify the conditional and the converse by yourself. If you did it correctly, you would say that the conditional would be, if a solution is a base, it has a pH greater than 7, and the converse is, if a solution has a pH greater than 7, then it is a base. In example 2, we're going to be given the conditional statement, but we want to write the converse and a biconditional statement from the original conditional statement. So here's your conditional statement. If a point is a midpoint, then it divides the segment into two congruent segments. So why don't you write the converse down? What would the converse be? The converse would be, if a point divides a segment into two congruent segments, then the point is a midpoint. And now we write our biconditional. we get rid of the if-then statement. And we would say a point is a midpoint if and only if it divides a segment into two congruent segments. That's it. A converse and a biconditional are really not that hard once you understand what a biconditional statement is. Now this is important. You need to write this down. For a biconditional statement to be true, both the conditional statement and its converse must be true. If either one of these is false, the biconditional statement is false. So if anything is false, whether it be the conditional or the converse, then the biconditional itself is false. So in this example, you're going to basically tell me, is it true or false? If it's false, give a counterexample. So let's start with A. A square has a length of 5 if and only if it has an area of 25. So let's start with our conditional. Our conditional, which I'm hoping you can do a lot of these in your head. Our conditional would say, if a square has a length of 5, then it has an area of 25. Is that true? If a square has a length of 5, then it has an area of 25. That would be true. Now let's do the converse. If a square has an area of 25, then its length is 5. So if a square has an area of 25, would the length be 5? Absolutely. So in A is true because the conditional and the converse are true. In part B, it says, the number n is a positive integer if and only if 2n is a natural number. So let's start with the conditional. We would say, if a number n is a positive integer, then 2n is a natural number. Now, a natural number is just a positive integer. So if the number n is a positive integer, then 2 times that number would also be a natural number. It would be a positive integer. Now, let's switch it around. If 2n is a natural number, then the number n is a positive integer. If 2n is a natural number, then it is a positive integer. No, that's going to be false. Here's why. We could say, okay, so remember, we're doing the converse. The converse says if 2n is a natural number. So we could say, okay, 2n is a natural number. Let's pick 1. So we're saying 2n is equal to a natural number, in this case 1. Well, what would the value of n be? N would be 1/2. So then we'd say if 2n is a natural number, which it is here, we picked 1, then the number n is a positive integer. Well, 1/2 is positive, but it's not an integer, it's a fraction. So therefore, we just proved a counterexample. This would be false. Now in geometry, biconditional statements are used to write definitions. Here's another vocab word. A definition is a statement that describes a mathematical object and can be written as true biconditional. Important. A definition can be written as a biconditional. Most definitions in the glossary are not written as biconditional statements. You never see definitions in the back of your book with if and then, if and only if. But they can be. The if and only if is implied, which means it won't say if and only if, but it implies that it can be written like that because it's a definition. A definition of any vocab word that you are writing is a biconditional statement. So let's do an example of that. Now, these are 3 vocab words that you should know. If you know them, there's no reason to write them down. But if you don't, it would be my suggestion that you write these down. So, here we go. You do not need to draw any of these pictures or anything. You know what a polygon and triangles are. In the glossary, here's what a polygon says. A polygon is defined as a closed plane formed by 3 or more line segments. Each segment intersects exactly 2 other segments only at their endpoints, and no 2 segments with common endpoints are collinear. A triangle is defined as a 3-sided polygon, and a quadrilateral is a 4-sided polygon. So you're probably asking yourself, Why in this section are we starting to talk about triangles and quadrilaterals? Here's why. I'm going to pick the triangle here. The definition of a triangle is a three-sided polygon. So you're like, okay, well that's easy. Let's write it as a biconditional. So first, let's write it as a conditional statement. You could say, if a polygon is a triangle, or if a figure is a triangle, then it is a three-sided polygon. That's true. I could then write a converse. If a shape is a three-sided polygon, then it is a triangle. We have just shown you that this definition is actually a biconditional statement. This first sentence is important. Make a note of this. A good, precise definition can be used forward or backwards. That means it's a biconditional statement. If you truthfully have a very good definition, it can be written as a biconditional statement. So let's use an example of the quadrilateral. For example, if a figure is a quadrilateral, then it is a four-sided polygon. There's your conditional statement. The converse, if a figure is a four-sided polygon, then it is a quadrilateral. To make sure this definition is precise, it helps to write it as a biconditional statement. You could write it as a figure is a quadrilateral if and only if it is a four-sided polygon. Our last example is this. I want you to write this definition in blue as a biconditional statement. So on your own, take the definition, a triangle is a three-sided polygon, and write it as a biconditional statement. Here's our biconditional statement. A figure is a triangle if and only if it is a three-sided polygon. The reason it's true is because the conditional statement and the converse are both true. And here's your vocab. Your vocab are these 5 vocab words: biconditional statement, definition, polygon, triangle, and quadrilateral.